بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Today we will talk about complex numbers, and in fact we're going to see an introduction about complex numbers. Let's begin with the first activity. We need to solve in N, Z, Q, and R each of the equations below. We're going to have a set of equations and we need to solve them. Let's see first the sets of numbers. This is N. It's a subset of a bigger set, which is Z, which is also a subset of a bigger Z, which is a Q, and Q is also a subset of a bigger set, which is R. Remember, R is called the set of real numbers, Q is the set of rational numbers, Z is the set of integers, and N is the set of natural numbers. Now we need to solve each of the following 5 equations in these sets. This is the first equation. It's of degree 1. If we isolate x, we get x is 3, and 3 in fact is a natural number. Consequently, it will be an integer, a rational number, and a real number. Now the second equation is also a first degree equation. So if we isolate x, we get x is negative 1. It's in fact an integer. Consequently, it will be a rational number and a real number. Now the third equation, it's also of first degree. If we isolate x, we get x is negative 10 over 3. This is not a natural number and this is not an integer because it's decimal. So this is a rational number. Consequently, it will be a real number. Now the fourth equation is of second degree. If we just expand and work it out, we get x is the square root of 2, or x is negative square root of 2. So consequently, this is not a natural number, it's not an integer, it's not a rational number. In fact, these are irrational numbers and they are going to be in the set of real numbers. Finally, this equation, you can see that it has no real roots. X squared can never be negative 1. So it's not natural, it's not an integer, it's not a rational number, and it's not a real number. And the big question here is, in part 5, what happens if we can find an imaginary number, let's call it I, whose square is negative 1? What will happen if the square of I is negative 1? What would be x? Try to think about this question. In fact, we're going to see that we will have a new set, which is the set of complex numbers that contains such cases, and it's usually denoted by C. Let I be an imaginary number whose square is negative 1, so I squared is negative 1, and A and B be two real numbers. So I is an imaginary number, A and B are two real numbers. Well, the set of numbers that have the form z equals a plus ib is called the set of complex numbers. It's denoted by this C, and a plus ib is called the algebraic form of z. So what is the set of complex numbers? It's the set of all numbers that could be written as a plus ib, where a and b are two real numbers and I is an imaginary number. Let's see some application about this definition. This is very easy, you will see. In each of the cases below, z is a plus ib, we need to find a and b. So this is z, we need to find a and b in each case. So in the first case, we can see that a is 1 and b is 2. b is the coefficient of I. Well, in the second case, a is 3 and b is negative 1, it's the coefficient of I. In the third case, we can see that a is 0 and b is 4. And in fact, a is 0 because 4i could be written as 0 plus 4i. Now, in the fourth case, a is negative 7 and b is 0 because negative 7 could be written as minus 7 plus 0i. And finally, a is half and b is negative the square root of 3 over 2. Now let's apply. In each of the cases below, we need to find z knowing a and B. This is A, this is B, and we need to write Z. Try to do it alone. Let's see, for the first one we get 3 minus 2i, just substituting A and B. The second case is minus 1 plus I. For the third case, it will be 6. And the fourth case is minus 5i. And the last one is negative radical 2 over 2 minus radical 2 over 2i. Okay, let's continue with the second example. We need to write z in algebraic form. Remember, algebraic form means a plus ib, so we need to simplify. If we just simplify here, we deal with complex numbers as if we are dealing with real numbers. In other words, what is 1 minus 3? It will be minus 2. And what is 2i plus 4i? It will be 6i. And this is the algebraic form, and in this form we can see that a is negative 2 and b is 6. The second case, try to expand as if you are dealing with real numbers. Just expand. Here pay attention, 8i times minus 2i is minus 8i squared. And try always to replace each I squared by negative 1. So this becomes a plus 8. Then we join them together. 1 plus 8 is 9. Minus 6 is 3. And 2i plus 12i is 14i. Now the third case, we can use also identities. This is a squared minus 2ab plus b squared, but we have to pay attention to I squared, which is negative 1, and we get minus 3 minus 4i. Now let's see the application. We need also to write z in algebraic form. Try to do the first one alone. We get 5 plus I. For the second one, we just expand. We get 8 minus 2i. And the third one, this is what we get when we expand, and the final answer would be 3 minus I. In fact, all of these details could be done using the calculator. Let's see how. This is the calculator that you have. We're going first to translate it into complex form. So we go to the mode, we press on the mode, and we can see here, this is complex, so we press on number 2, and you can see on the screen of the calculator that the word complex appears somewhere here on the screen. By now, the calculator can understand complex numbers. Let's say I want to simplify the first part, which is here, part A. We write 1 plus 2i, this is I as you see, minus 3 plus 4i with an equal sign, and this is the answer, which is minus 2 plus 6i. That's it. Now, if I want to choose another example, let's say I want to do part C here in the application. We open parentheses, we write 1 plus I, close parentheses, into 1 minus 2i, close parentheses, then equal sign, we get 3 minus I, and this is the answer as you see. So we can do all of these details using the calculator. We don't have to do all the calculations. Let's continue. What are the real part and imaginary part of a complex number? A and B are two real numbers. As usual, Z is A plus IB. Well, this A is called the real part of Z, and it's denoted by capital R, small e, open parenthesis Z, close parenthesis is A. So A is the real part of Z, and this B is called the imaginary part of Z, and it's denoted by capital I, small m, open parenthesis Z, close parenthesis. So each complex number has a real part and an imaginary part. A would be the real part, and B would be the imaginary part. Let's see the properties. A complex number z is said to be real if and only if its imaginary part is 0. Let's say this is a complex number. If the imaginary part is 0, we're not going to have any I in the expression, so this number would be a real number. And a complex number is said to be pure imaginary. We call this number pure imaginary, not imaginary, if and only if its real part is 0 and its imaginary part is never 0. So here we have two conditions. And let's also imagine it. If the real part is 0 and the imaginary part is not 0, we're going to have a complex number that only contains I with a certain number, and this would be called a pure imaginary number. So till now, the real part of z is a, the imaginary part is b. Z is real if and only if its imaginary part is 0, whereas z is pure imaginary if and only if its real part is 0 and its imaginary part is never 0. Let's see this example. In each of the following cases, we need to find the real part and the imaginary part of z. So we need to specify the real part and the imaginary part. And in case we have x and y, remember that they are two real numbers. This is z. Try to find the real part and the imaginary part. Remember to write z in algebraic form first in order to tell. So in this case, we can see that the real part is 0 and the imaginary part is 2 minus 3x. Now, this case, we also try to write it in algebraic form. In other words, we collect the real parts alone, the imaginary parts alone. So the real part would be 4y plus 1, and the imaginary part would be minus 2 plus x. In this case, in fact, we just have a real part. The imaginary part is 0. So this is a real number. And this case, this is z. We try to take I as a common factor in order to show the imaginary part. So the real part is x plus y and the imaginary part is also x plus y. Now this case, well, the real part is x plus y over this quantity and the imaginary part is x minus y plus 1 over this quantity. Let's try to apply. We also need to find the real part and imaginary part of each of the following numbers. Try to do it alone. Well, in this case, it's organized. It's written in algebraic form. So the real part is 2 plus 3x and the imaginary part is minus 2y. Try to do this case. Also, if we just take I in common, the real part would be 2x plus y and the imaginary part would be minus 2x minus 2y. Now this case, so we try to divide it into two parts, x plus y over this quantity plus minus y over this quantity, and we can replace this plus by a minus. We just put this minus somewhere here. So in this case, the real part would be x plus 1 over this quantity and the imaginary part would be minus y over the same quantity. Let's apply more. M is a point whose coordinates are x, y, where x and y are two real numbers. The question is to find the set of points when the given condition is satisfied. We need the set of points M. Where does M move? Now, this is the expression, and we know that the real part of z equals the imaginary part of z. Try to do it alone. Well, in this case, the real part is 2x plus 3y, and the imaginary part is 3 minus x. If they are equal, we just write the two expressions to be equal. We get y is minus x plus 3, and we took it previously that in this case, M would move on the line with the equation y equals minus x plus 1. Now the second case, and we know that z is real. Try also to do it alone. Well, z is real from here means that the imaginary part is 0, and the imaginary part in this case is x squared plus y squared minus 9. So if we write this equation, this is what we get. And in this case, we also saw it previously, that m moves on the circle with center O 0, 0 and radius the square root of 9, which is 3. Now the third case, we know that z is pure imaginary, and this is what we have. Try also to do it alone. Well, z is pure imaginary from this property if the real part is 0 and the imaginary part is never 0. So here we have two conditions. Well, the real part is x plus y plus 2, this is 0, and the imaginary part is negative y is never 0. If we just try to simplify, we get y equals minus x minus 2, and y is never 0. So mainly m moves on this line, but let's see what do we do for this condition. So we state that m moves on the line with equation y equals minus x minus 2, deprived of the point minus 2, 0. And deprived means except this point. So m will move on this line except on this point. Well, how do we calculate this point? If we just suppose that y is 0 and we put 0 here, we get x equals negative 2. So we have a point whose coordinates are negative 2 and 0, and we have to exclude this point from the set of points. Now Rima, Rami, or Mira. X and y are two real numbers. Z is a complex number such that z is 3 plus ix over x squared plus y squared. The question is to find the real part and the imaginary part of z. Let's begin with Rima. This is the expression. Well, Rima wrote the expression as 3 over this quantity plus, she took I in common here, and she put 1 plus x over this quantity I, and she said that the real part is 3 over, and the imaginary part is 1 plus x over. Rami wrote the expression. He also wrote the real part here, the imaginary part here. He answered that the real part is the first part, and the imaginary part is the second part with an I. Try to see the difference between Rami's method and Rima's method. Finally, Mira, she also wrote the expression. She wrote 3 plus I over this quantity plus x over this quantity multiplied by I, and she wrote the real part as follows, and the imaginary part as x over x squared plus y squared. Well, it's very clear that Mira's method is not correct because a real part cannot have an I. And we can also state that Rami's method is not correct because remember, the real part and the imaginary part cannot have any I, and this I would be the problem. And I think that Rima's method is correct. Thank you.